Welcome to this particular lecture, and in this lecture we will see another application of operational amplifier. In the previous lecture we have seen the characteristics, then we have seen the circuits, and then we have seen how we can design those circuits for different generation of waveforms, for example integrator and differentiator. And during the integrator and differentiator I told you that they can be used as a filters, right. So, how we can use operational amplifier as filters and what exactly filter means, right. So, for us if you think about a filter for a human body, nose is a filter, right. Just to give a quick example, nose is a filter, right. So, same way if we talk of example of a tea, then the mesh that we use to filter out the milk or the tea from the tea leaves, right, that is a filter, that is a filter. So, same way so what does exactly filter means? Filter means that the thing or a system or a tool or a device that we can use, right, or a organ, right. If you talk about humans, it is a organ. So, it is a anything that can help us to remove the unwanted signals, unwanted things, right. So, filter will filter out the unwanted signals when you talk about electronics, and it will help us to get the wanted signals. It will allow the wanted signal to pass and unwanted signal to block or stop, right. So, today let us see how we can design different kind of filters using the operational amplifier. So, when I talk about operational amplifier, you guys now know the characteristics of op amp. So, it will be easier for you to understand how you can design the filters. Now, filters are of several types when we are going to discuss in this particular lecture based on the components we use and also based on the frequency they are operating at, whether it is a low pass filter, whether it is a high pass filter, whether it will only pass the band of frequency, whether it will only reject a particular frequency. So, depending on that we name the filters as well, right. So, let us see what exactly filters are and how can we design the filters using the operational amplifier. So, this is our class number 11 and we will look at the filters. We will see what are the filters. So, when you see the definition of filter is extremely simple. Filters are circuit that are capable of passing signals, you see, capable of passing signals within a band of frequency. It will only allow the band of frequencies to pass while rejecting or blocking signals of frequencies outside the band, right. So, if you select a band of frequency that you need to pass and you want to reject or block the signals outside the band, you can use the filters, alright. This property of filter is also called frequency selectivity. It is also called frequency selectivity because you are selecting a particular frequency from the band of frequencies or from the total frequencies, right. Now, next is filters can be passive, filters can be active. Filters can be passive, filters can be active. So, what do you mean by passive filters? The circuits built using RC, RL or RLC, right, either using the resistor and capacitor or resistor and inductor or resistor, capacitor and inductor, then these are called the passive filters, right. We already have seen what are passive components, what are active components, these are the passive filters, right. Now, when we talk about active filters, the circuit that employ one or more operational amplifiers or any other amplifier, okay, in the design and in addition to the resistors and capacitors, right, in addition to the resistors and capacitors, then that will be your active filter, that will be your active filter, right. Now, if you see what are the advantage of active filters, why we have to use active filters, right, why we have to use active filters, why we cannot generate the circuits using passive filters, then we have to understand what are the advantages of active filters over passive filters, what are advantages, okay. Let us see one by one. The first advantage is that active filters can be designed to provide require gain. We can change the gain in active filters, hence no attenuation as in case of passive filters. If we use passive filters, there will be attenuation and there will be loss. So, we can use the active filter and we can provide the gain, that is the advantage number 1. Second advantage is there is no loading problem because of high input resistance and low output resistance of op amp. We have seen the op amp characteristics, two characteristics of op amp, that is the high input impedance and low output impedance, correct. This is what we have seen, high input impedance and low output impedance. So, because of this characteristics, this will help us to remove the loading effect, and we will see what is loading effect in the experiments as well, alright. We will see how the loading effect can be removed when we perform the experiments. So, the advantage is when we use op amp, then the loading effect can be avoided. So, no loading problem in case of active filters. Third advantage over passive filter is the active filters are cost effective, as wide variety of economical op amps are available. If you buy a op amp 741 mu 741, right, in a bulk, it will give you about 10 INR, 10 to 15 INR per piece, right. So, you can buy in a bulk and it is really cheap. So, why not to make up active filters when we can we do not have to spend that much money, and in advantage we cannot see any loading effect and we can also change the gain. So, if there are this many advantages of active filters over passive filters, one will always go for the active filter, Okay. Now, what are the applications then? What are the applications of active filters? Active filters are mainly used, you see, mainly used in communication and processing circuits and signal processing circuits. So, all the or most of the communication based applications, we will see the use of the filters, and in particular active filters. They are also employed in wide range of applications such as entertainment, medical electronics, etc. Alright. So, how can we design a filter, or how we can use the filter in medical electronics, that can be a part of another lecture itself or another course itself, but we need to understand that once we understand how we can use operational amplifier as an filter, then where it can be used and what are the applications. So, main application of filters are in communication circuits, right. So, that means that when you see any communication circuit, you try to see whether it has some active filters or not. Same way signal processing tools, same way electronics, same way for entertainment purpose. When say entertainment, what does entertainment means, right. Is it means that we are playing a video game, and in the video game the circuit that we are designing has some filters in it, right. So, what are the applications of filters, that also we should know, right, and we will see some of the advantages that I have just talked recently or right before 2 minutes, that are the low loading effect. So, how loading effect can be removed if we use active filter over passive filters, we will see in the experiment part as well, alright guys. So, now let us see what are the 4 basic categories of active filter. What are the 4 basic categories of active filter? First category is low pass filter. First is low pass filter, second one is high pass filter, third one is band pass filter, fourth one is band reject filter, right. 4 categories: low pass, high pass, band pass, band reject, right. Each of these filters can be built by using op amp as the active element combined with RC, RL or RLC circuit. Second, digital filters are implemented using digital computer or special purpose digital hardware. Now, there are 2 types of filter based on based on whether it is analog or whether it is digital. So, it can be analog filters, it can be digital filters. Now, also based on the type, based on the category, there are 4: low pass, high pass, band pass, band reject. But if you want to form a digital filter, it can be implemented using a digital computer, or it can be also implemented using special purpose digital hardware. While analog filters may be classified either as passive or active, right, and are usually implemented using R, L and C components and operational amplifiers. Alright. So, main two categories of filter is digital and analog. Further in analog you can have active as well as passive. In terms of it four categories, basic categories, it can be divided into 4 parts. One is low pass filters, high pass filters, band pass filters and band reject filters. We will see each of them. We will see each of them in this particular module. Okay. So, let us see basic filter response for the low pass filter. Alright. So, what does low pass filter means? Low pass, right, that means it will pass the frequencies which are low frequencies. So, we can if you want to, if you have let us say 0 to 1 kilohertz frequency, okay, and I want to only pass a frequency from 0 to 200 hertz and any frequency above 200 hertz should not be passed, then I can design a low pass filter, right. It will pass the low frequency, it will block the high frequency. Now, this high frequency, which one is high frequency, that we can design the filter and according to our design it will allow the low frequency to pass, it will attenuate the frequency above certain frequency, or what is that frequency, that is called critical frequency FC. We will see in this module as well. Okay. So, if you come back to the screen, what you see is a low pass filter allows for easy passage of low frequency signals, easy passage of low frequency signals from source to load, from source to load. So, you see here, this is a circuit. When you see here, what is that? There is a source, there is a resistor R and there is a capacitor C. So, just using R and C you can form a low pass passive filter using just component R and C, just using components R and C you can find a low pass filter that is your passive filter. Now, a low pass filter allows easy passage of low frequency signals, but difficult passage of high frequency signals. So, if you see ideal curve, ideal plot for the low pass filter or ideal response of the low pass filter, it will look like this. You have y axis where you have gain and you have x axis where you have frequency, right, x axis where you have frequency. Okay. And then you have to design the filter such that above the frequency FC or FH, right. So, it will not allow the frequency to pass, only frequency below this frequency will be allowed to pass. So, the frequency, so you can see a sharp cut like this, right, and it looks like a wall, right. So, wall from this side or from this side also, correct. So, sharp change, right, because we want to only allow the frequency within this particular band and any frequency above this band, this one should not be allowed to pass, right. So, this frequency is allowed to pass, that is why it is called pass band. This frequency is not allowed to pass or band of frequency is rejected, it is called stop band, right. You can pass the frequency, you can stop the frequency. This is an ideal response of the low pass passive filter or low pass active filter. You will have the same response, but it is ideal response. But when you see actual response, what you will see lot of things. That first is, you see there is a the cutoff frequency should be here. It should have, actually it should have like this. This is the ideal plot. But in reality, in practical, when you perform the experiment, the actual response would be different than your ideal response. And here what you see? Here you see that it will go slowly and it will stop at certain frequency, right. But we will consider only frequencies that are allowed are about -3 dB, or 70% of the total voltage. This is the pass band as we have seen, and this is the bandwidth, and this is the frequency, this is the gain, right. Y axis is gain, x axis is frequency. Now, this one, this slope, right, this slope is called roll off rate, alright. So, this is a response of single pole RC filter, and this is a transition region where you can see here, this is a transition region, this slope itself is a transition region, and the roll off rate for this one is -20 dB per decade. minus 20 dB per decade, right, and this one is nothing but your stop band region. It is nothing but your stop band region, alright. So, now you have seen 2-3 words. First word is transition region. Transition region is from pass band to stop band, transition region. Second is response of single pole RC filter. What is single pole RC filter? There is only one R, there is only one C. If I keep on increasing the resistors and increasing the capacitors, there will be 2 pole RC circuit, 3 pole RC filter, and so on and so forth, alright. So, for single pole RC filter, my roll off rate is minus 20 dB per decade. For 2 pole RC filter, my roll off rate will be minus 40 dB per decade, and so on, alright. And you will we will see when we see the 2 pole RC circuit, alright, and this is your stop band region where the frequency would be stopped. So, a low pass filter is a filter that passes frequency from 0 Hz to the critical frequency. Critical frequency, I said it can be denoted by FC, here it is denoted by FH, right, is critical frequency FC, and significantly attenuates all the other frequencies, Any frequency above the critical frequency, it will attenuate. Attenuate means it will not allow to pass, okay. So, this is your low pass filter response. Now, if you see this is again same graph, same plot. So, pass band of a filter, what is pass band? This is a pass band, right. So, pass band of a filter is the range of frequencies that are allowed to pass through the filter with minimum attenuation, minimum loss, alright, and usually it is defined there less than minus 3 dB of the attenuation. Transition region. What is transition region? Transition region shows the area where the fall off occurs, right. This is, you see, from here now the fall off is occurring, right. So, it is a transition region. Stop band is a range of frequency that have most attenuation. You see here the maximum attenuation occurs here, it is a stop band, right. And finally, we have critical frequency, very important term, critical frequency, also denoted by F subscript C, also called cutoff frequency, right, because this frequency, you see this one is a cutoff frequency, because above this frequency the response the frequency would not allow to pass, and in the actual response you will see that slowly it is going to the region where frequencies are minimum number of frequencies are allowed to pass. Right. So, critical frequency defines the end of the pass band and normally specified at the point where the response drops to minus 3 dB or 70.7% from the pass band response, right. 70.7% of the pass band response when this falls here, right, and the critical frequency is nothing but the end of pass band here, right, and it will be nothing but 70.7% of the pass band response, or we can say minus 3 dB, alright. So, these are the regions within a filter. Now, if I want to design this filter, it is very simple. I use one resistor, I use one capacitor, I apply a voltage, and what I see is that you know the formula Xc equals to 1 upon 2 pi Fc for capacitor, right. So, what will happen for low frequency? The capacitor would be not conducting, right, it will not conduct. So, what will happen that at low frequency Xc is very high, right, it is very high. Why? Because the frequency is very high. So, Xc is 1 upon 2 pi, frequency is very low, right, frequency is extremely low. Why? Because we are passing low frequencies, right. So, for low frequencies Xc would be high. When Xc is very high, capacitor consider as an open circuit. So, that means that it is not there, it is not conducting, right, it is open circuit. So, you have to see on the screen please, when the capacitor is not conducting, you can see here, right, that means it is an open circuit. So, whatever signal is there in the input with a lower frequency, you will see at the output, right. So, low pass at normal frequency, right, low pass at DC frequency is infinite, Xc would be infinite, right, DC is what, f equals to 0, DC signal is frequency is 0. So, Xc would be nothing but infinite, right. Under this condition VO equals to V in or AV equals to unity. You can see here in this particular condition low pass from 0 to certain frequency, that is our FC, it will pass the frequencies, and what will happen at very high frequencies, XC is very low and VO is small as compared within V in, hence the gain falls and drops off gradually as the frequency is increased, That means that if I keep on increasing the frequency, my Xc will keep on decreasing, and that means that it is considered now as a shorted, right now it is not conducting, right. In this case at lower frequency it was not conducting, now it is completely shorted, because at high frequency the Xc would be less, and that is why it is shorted. That means the output you will see slowly fading down, and finally there will be no frequency that can pass through this particular circuit. Alright, easy, extremely easy. So, you have to just understand the role of the capacitor. If you understand the role of capacitor, the filter becomes very easy to understand, right. The filter becomes extremely easy to understand. Alright. The bandwidth of an ideal low pass filter, is equal to Fc, So, bandwidth is equal to Fc, right. The critical frequency of a low pass filter occurs when Xc equals to R and can be calculated using the formula Fc equals to 1 upon 2 pi Rc. That means that if I design a filter, then what will I have? A resistor, I will have a capacitor, and then I will have output voltage VO, correct, C, R, signal, right. So, depending on the value of R, depending on the value of C, I can select my critical frequency. Critical frequency is frequency at which the attenuation starts, right. We have seen, right, we have considered this minus 3 dB like this, isn't it, right. So, critical frequency of a low pass filter RC filter occurs when Xc equals to R and can be calculated using the formula Fc equals to 1 upon 2 pi Rc, Now what to do? Let us see, alright, let us see. So, until here what we were looking at low pass filter, but that were passive filters. Passive filters means if this was not there, op amp was not there, right. We were looking only on this circuit where resistor and capacitor was there, correct. Now we are looking at low pass active filter, When you have to have low pass active filter, you have to have a amplifier, and if you use here, what is amplifier? The amplifier is nothing but unity gain amplifier. We have seen the op amp, right. We have seen the circuit of op amp when it was used as a buffer, right, unity gain amplifier, or voltage follower, right. These three things we have seen, all three things is same circuit which is right shown here, right, buffer, unity gain amplifier or voltage follower, one and the same, right. So, now if I connect a unity gain amplifier with a low pass filter which is my RC filter, it becomes my active filter. So, the first order low pass active filter consists simply of RC filter stage providing a low frequency part to the input of non-inverting operation amplifier. It is what, inverting or non-inverting? It is non-inverting because the signal is applied to the non-inverting terminal of the operation amplifier. So, this is the RC filter, whatever the output is here, we were measuring output here, right, VO, this output is with respect to ground, right. So, this is ground. If I have told you earlier also, if you do not see a ground, assume that there is a ground, okay, and then with respect to ground, this is a voltage that is generated, that is fed to the non-inverting terminal of the operation amplifier, right, it is fed to the non-inverting terminal. So, that is what is written, the active filter or first order low pass, first order, always remember I have told you first order, second order, right. The first order low pass filter and that too active filter consist of RC filter stage providing a low frequency part to the input of a non inverting operation amplifier. The amplifier is configured as a voltage follower or a buffer or a unity gain amplifier, giving it a DC gain of 1, right, or AV equals to plus 1 or unity gain as opposed to previous RC filter which has a DC gain of less than unity, right. So, just RC filter will have DC gain of less than unity of course, but when we use a unity gain amplifier we will have a DC gain of 1. The advantage of this configuration is that op amp's high input impedance prevents excessive loading. You see, high input impedance prevents excessive loading of the filter's output, while its low output impedance prevents the filter cutoff frequency point from being affected by changing in the impedance of the load, right. Advantage, right. First advantage is high input impedance that will prevent the excessive loading, right, and second would be the low output impedance which prevents the filter cutoff frequency from being affected by the changes in the impedance of the load. If I connect this further and if I change the load, right, it will not be affected because I have low output impedance of this particular amplifier, alright. The load resistors, if you change it, it will not affect the filter response. While this configuration provides a good stability to the filter, its main disadvantage. So, what is the drawback, right? What is the drawback? Let us see what is the drawback. So, the drawback is or disadvantage is that it has no voltage gain. You see why? Because whatever voltage you apply here, right, which is the output of your filter. So, I will say VF, okay, output of filter. Then when we see V out will be similar to VF because the voltage gain is, it is a unity gain amplifier. So, voltage gain is 1. So, that means that there is no actually voltage gain in the output of the operation amplifier, that is a disadvantage, right. However, although the voltage gain is unity, the power gain is very high, right, because it can follow the voltage, but it will also increase the current, it will increase the current. So, power is very high as its output impedance is much lower than its input impedance. If a voltage gain greater than 1 is required, we can use the following circuit. Which circuit? So, if I want a voltage gain, that means my V out should be some gain into Vf, whereas my gain can be 10 into Vf. So, how can I have 10? I cannot use this circuit, right. I have to use another circuit. What is that another circuit? Another circuit is active low pass filter with amplification. Active low pass filter with amplification. So, what is low pass filter? Low pass filter is shown here, right, and here I have connected a non inverting amplifier. You see here what is my circuit? Non inverting amplifier, correct. So, frequency response of a circuit will be same as that of the RC filter, except that the amplitude of the output is increased by the passband gain AF, right. So, we can have DC gain of R1 R2 by R1 1 plus R2 by R1, right. Why? Because we have seen in non inverting amplifier our DC gain is 1 plus R2 by R1. If I use inverting amplifier, I will have DC gain of R2 by R1, that will be my gain, right. So, for the non inverting amplifier, I have a gain of 1 plus R2 by R1. Thus, by changing the value of R2 and by changing the value of R1, I can decide what will be the gain of this particular filter circuit, and thus it becomes active low pass filter with amplification, right. So, therefore, the gain of active low pass filter as a function of frequency will be voltage gain equals to V out by V in equals to AF under root of 1 plus FC by FC whole square. This you have to remember, this is a voltage gain of the active low pass filter, alright. Now, there is a derivation to derive this, we are not interested in deriving this particular equation, alright. But I can always tell you which book to refer if you want to understand how this equation is derived, right. So, you can ask me if you are interested to understand how this equation is derived. If not, you should understand that how you can implement the circuit, how you can design the circuit. That is the idea of this particular course, that you at the end of this course you are able to design the filter circuits, design several circuits, analog circuits using operation amplifier, using MOSFET and so on and so forth. So, let us go back here, where AF in this particular case, AF is the pass band gain of the filter, F is the frequency of the input signal, FC is the cutoff frequency, alright, this we know, correct. So, thus the operation of a low pass filter can be verified. So, at very low frequencies F less than FC, my output will be VO out by V in equals to AF, right. You see this one, if my F is less than FC, F is less than FC in this particular case, right, then my V out will be nothing but AF, right, V out would be nothing but AF. At F equals to FC, my V out would be V out by V in would be AF by root 2 or 0.07 AF. At high frequency it will be less than AF. This is very simple, right, you will find in lot of books same equations, correct. Thus, the active low pass filter has a constant gain AF from 0 hertz to high frequency, cutoff point FC. At FC the gain is 0.707 of AF, and after FC it decreases at constant rate as the frequency increases. This is similar thing what this graph shows. It is a gain versus frequency graph, FC, right, frequency is given in hertz, gain we calculate in terms of decibel, right. So, when the frequency is increased tenfold, that is the voltage gain is divided by 10, at that time the FC is decreased at a constant rate. In other words, the gain decreases each time the frequency is increased by 10, the gain is increased, right, or gain is decreased by 20 decibels each time the frequency is increased by 10. When dealing with the filter circuits, the magnitude of the pass band gain of circuit is generally expressed in decibels or function of voltage gain, and it is given by this particular equation which you can see here. Magnitude of voltage is nothing but A equals to 20 log V out by V in or minus 3 dB, right, magnitude of voltage gain in decibels. So, minus 3 dB equals to 20 log 0.707 V out by V in, correct. So, this is how you can derive the formula for the magnitude of voltage gain in case of the low pass active filter, alright. Now, let us see second order low pass active filter. So, now if I increase one more capacitor and one more resistor, right, it will become second order. There are 2's R and there are 2C, gain remains same, AB equals to 1 plus R2 by R1, but my frequency formula earlier for single order was 1 upon 2 pi RC, right, FC equals to, you see where is it, FC equals to 1 upon 2 pi RC. If I use this, right, then my frequency formula becomes FC equals to 2 pi, right, here in this case R1 C1 R2 C2. So, FC equals to 1 upon 2 pi. Now, I have under root of R1 or R3 in this case, right, in this case let us say R3 R4 C1 C2. So, if I have R3 equals to R4 and C1 equals to C2, then my FC will be 1 upon 2 pi under root of R square C square or 1 upon 2 pi RC, correct. What I am saying is that if you see this circuit and if you see the formula for the critical frequency, the formula for critical frequency is FC equals to 1 upon 2 pi under root of R3 R4 C1 C2, which is this particular circuit. It does not matter R3 R4, I can say R1 R2, does not matter, right, I can say C11 C121, that does not matter. Point is there are 2 resistors, 2 capacitors, and then there is of course this inverting amplifier, there is a non-inverting amplifier, right, there is a non-inverting amplifier. The gain of non-inverting amplifier is AV equals to 1 plus R2 by R1, the frequency formula is 1 upon 2 pi under root of this particular 2 resistors and C1 and C2. Now, if what I say is that if I have R3 equals to R4, right, in this particular case R3 equals to R4 and C1 equals to C2, my FC, this particular formula will become 1 by 2 pi r square C square, because R1 equals to R4, C1 equals to C2. So, that means FC will be nothing but 1 upon 2 pi RC, 1 upon 2 pi RC, right, which is similar to my first order low pass active filter, right. Critical frequency formula becomes similar to my first order low pass active filter. Anyway, let us see. As with passive filter, a first order low pass active filter can be converted into second low pass active filter by using additional RC network. The frequency response of the second order low pass active filter is identical to that of first order, except that the stop band roll off rate will be twice the first order. That means, if you see the first order filter, you will see 20 dB per decade, right. That was the formula, right, that the roll off rate was nothing but 20 dB per decade. In case of, this is for the first order low pass filter. In case of second order low pass filter, my roll off rate, right, will be 40 dB per decade, 40 dB per decade. Okay. So, that is what is written, that the roll off rate increases. So, if I keep on increasing the roll off rate, my filter first response was this. If my roll off rate is increasing, the response would be similar to this. Still my roll off rate is increasing, response will be this. This is my ideal response, right. This is my ideal response, it should look like this, right. So, increasing the roll off rate, that means that my actual response is getting closer to my ideal response. My actual response is getting closer to my ideal response. Always remember, when you plot the graph, y axis is gain, which can be in decibels, x axis is frequency, this is your critical frequency FC, this is your frequency F, is always in hertz. So, you have to write hertz, you have to write gain, write always unit. Okay. Always you have to plot, when you plot the graph, always write units, very important, very important. Okay. Anyway, so let us go to the next line, that is that the frequency response second order low pass filter is identical to that of first order, except that the stop band roll off rate will be twice of the first order low pass filter, which is 40 dB per decade. Therefore, the design step required for second low pass order filters are the same. Okay. So, this is the circuit and this is the formula. Now, if I use this is an example. You see, if I have a cascaded voltage gain, when cascading together filter circuits to form high order filters, the overall gain of the filter is equal to product of each stage. For example, gain of the stage may be 10 and gain of stage may be 32 and the gain of third stage may be 100, right. So, for example, what is saying that if I cascade my filters and my first stage is 10, second stage is 32, third stage is 100, these are gain, right, then the overall gain would be 32,000, because 10 into 32 into 100, correct. So, AV equals to nothing but AV1 plus AV2, sorry, AV1 into AV2 into AV3. So, AV equals to 10 into 32 into 100, 32,000. So, AV in decibel 20 log 32,000, that will be 90 dB, right. So, if I see 90 dB, that means that 90 would be nothing but 20, 30 and 40, correct. 90 dB would be nothing but 20 dB plus 30 dB plus 40 dB. Very easy cascading voltage gain in case of the filters, Now, number of filters can be increased by cascading, right, number of filter poles, that is from 1 RC to 2 RC to 3 RC. Here you can see 3 R and C, right, 1 RC, 2 RC, 3 RC, right. That means it is a 3 pole or third order low pass filter. To obtain filter with 3 poles, cascade 2 pole filter with 1 pole filters. Easy, very easy, right. Let us see now example of low pass filter. So, you see here the circuit is given. Okay. So, what is the question? Design a low pass filter for a high cutoff frequency of 2 kilohertz, alright. So, we have to design a filter for the cutoff frequency FC is given what, 2 kilohertz, okay, and pass band gain, right, pass band gain is given 2, right. Where is the input? Input is here, You see input is here, where is it? On the non inverting terminal. So, this looks like non inverting amplifier, correct. So, non inverting amplifier, what is the DC gain? 1 plus what is the here feedback? RF and RI, 1 plus RF by RI, this we know, right, this we know. So, FC is given, R is given, right, where is R? R is 1 kilo ohm, right, C is also given. So, FC equals to 1 upon 2 pi RC, right, we know that, right, this formula. What is the formula for the first order low pass filter for critical frequency? FC equals to 1 upon 2 pi RC, we know it, beautiful. Then C will be implies C equals to 1 by 2 pi R into FC, right, C equals to 1 upon 2 pi R into FC. So, when you solve this, when you substitute the value, you know value of FC, you know value of R, then you get C equals to 70.95 79.57 nanofarad, or this is the value, right. Required passband gain is 2. So, that means we have formula 1 plus RF by RI equals to 2, correct. Now, if that is the case, that means my RF by RI would be 1, 2 minus 1, right. Now, what is my RF? I do not know, right, I do not know. Suppose we have to design it, right, because design a low pass filter. So, suppose these things are not given, and you are only given the value of R, right, or that is also not given, let us say that is also not given, then how can you design the filter? How you can design the filter, right? Only if I give you this particular problem, that you have a cutoff frequency FC of 2 kilohertz and gain of 2, based on that how you can design the filter. So, now since we know FC equals to 1 upon 2 pi RC, we can say let us R equal to 1 kilo ohm, right, and then C we can find, then we can substitute. So, R and C is available. Now, 1 plus 2 pi 1 plus RF by RI, that is your non inverting amplifier gain, when we substitute the value of RF and RI. So, we do not know value of RF and RI, but we know value of gain. So, we know that RF by RI will be equal to 1, because 1 plus RF by RI equals to 2. So, RF by RI equals to 2 minus 1, it will be 1. So, that means that RF right should be equals to RI. We can take any value, let us say 10 kilo ohms. So, now you have value of RF RI, you have value of C, you have value of R, and then you can be based on this particular values, you can design this low pass filter, low pass active filter, right. Easy, super easy, right. Let us take one more example, if that was easy. In the circuit shown figure, so now if you are given a circuit, R equals to 3.3 kilo ohm is already given, right, C equals to 0.047 microfarad, both capacitors are same, Ri also given 27 kilo ohm, Rf is also given 20 kilo ohm. Calculate the high frequency cutoff or FH and pass band gain AO. Two things you have asked, one is to find the cutoff frequency. So, Fc equals to, or high cutoff frequency can also be denoted by Fh equals to 1 upon 2 pi Rc. I have all the values, because you see R is just R, it is given, right, R, that means that this both resistors should be equal, sorry, R is given, which is your 3.3 kilo ohm, right, and then your capacitor C is given 0.47 this one. So, now if I substitute the value, I will have 1 upon 2 pi, what is R? 3.3 into what is C? 0.047 microfarad, 0.047. So, this is not 1 kilo ohm, you consider this also as 3.3 kilo ohms, alright. So, what will be the answer? Answer will be 1.026 kilohertz. What is that? My FH, that is my high cutoff frequency. Now, what I am asked? I am asked to find the passband gain. What is passband gain? Well, this is again your non inverting amplifier. We know the passband gain Rf by Ri. Value is given, yes. Ri given, yes. Very easy. Gain equals to this particular formula. Substitute the value and you will see gain of 1.74. You will find the gain of the low pass active filter. you will find the gain of the low pass active filter. Alright guys. So, the point is given the values you can design a circuit, right, and given a circuit you can find out the values. Both ways now you can do it. Given a values you can design a circuit of a filter, and given a circuit you can find the values of the filter. What are the values of the filter? Cutoff frequency, gain, resistors, capacitors, correct. So, in this particular module what we have seen is low pass filter, we have seen the passive filter, we have seen the active filter, we have seen the some of the examples of low pass and low pass active filters, right. Now, in the next module what we will see? We will see the how the high pass active filters can be used, how we can use the high pass active filters. Okay. So, I will see in the next module, and let us see how we can design the operation amplifier, how you can design the high pass active filters using the operation amplifier. Alright. Till then you just look at the things that I have taught you in this particular module, and I will see you in the next class. Till then you take care.